So I'm Henri. Thought I'd give a quick introduction for those who either haven't watched our stream before or haven't watched in a while. We haven't done a stream for about 3 or 4 weeks now, and we're just getting started up. So we used to go by Climate Fortnite, and we started really by streaming Fortnite and talking about climate change, and now we're moving out of just Fortnite and playing other games. So on Tuesdays, I play games that have to do with climate change, and then on Sundays, we do more sort of traditional science communication content. So we'll be talking about recently published climate science papers. I'll be doing interviews with other climate scientists, and just general Q&As and discussions with chat about topics they're interested in. So a little background about me. I'm a PhD student at MIT getting my doctorate in climate science and also oceanography. I'm a third-year student now, and I passed we have this exam after 2 years, which qualifies you to be a PhD candidate. So I just passed that a few months ago. So now starting to work on my dissertation. And I've been a passionate gamer my whole life, and always loved the Twitch community, watched a lot of streams throughout my days. So thought it'd be fun to contribute the stuff that I work on and the stuff that I know really well to the Twitch community. And hope there's like-minded people out there who care about climate change and also like gaming. So I might wait a couple minutes before I start talking about this paper. But the plan is to talk about 3 different papers tonight, and they don't explicitly have anything to do with each other, but they are 3 recently published papers in the past couple weeks or months, and they all have to do with climate change in the future. And the first one has to do with past climate change and how we think about that in terms of the future. The second one has to do with how the economy is affected by climate change, and actually how the economy feeds back to affect climate change, which is kind of an interesting question. And the third one, which if we have time to get to, is about the deep Pacific Ocean, which is sort of my field of study for my PhD. And it's an interesting question about what the temperature trends are there in the Pacific. You might think that because of climate change, the Pacific should be warming, but actually the question or the answer is a little more complicated than that. So we'll get into the details. All right, so maybe I'll get started on this, unless anyone has any questions up front about me or the stream or anything like that. And I'll be reading chat throughout. So if you have any questions, feel free to interject, and we can get to them. So this is a paper called Pliocene and Eocene Provide Best Analogs for Near Future Climates. So the Pliocene is this period about 3 million years ago. And the Eocene is a period much further back, about 50 million years ago. And these were really warm climates. The Eocene was warmer than the Pliocene. And so the idea behind this paper is that, humans have lived in a pretty mild climate over the past 2,000 years, especially where climate hasn't really changed that much. The temperature of the planet has been pretty constant. But we know that over the past 50 or so years, we've warmed by a decent amount. Anywhere between 0.5 or 1 degree Celsius, depending on how you define things. And in the future, we expect that we're going to warm anywhere from 1.5 to 8 degrees Celsius, depending on how much CO2 or carbon dioxide we put in the atmosphere. And so the question of this paper is, okay, if we're going to warm in the future because of human-caused greenhouse gas emissions, and we know the planet's been warm in the past, basically, which past climate is most similar to the one we're going to experience in the next couple hundred years? It's a pretty neat idea. And one of the reasons you'd want to do this is because we know a lot of things about the past. And so there are things you can learn from the geological record, which you just can't learn from something like a climate model. So, for example, if you find a geological analog, so let's say 50 million years ago, you think is going to be similar to what the future is going to look like. Well, you know what kind of animals lived back then because you have the fossil record. You know something about, where different trees like to grow. You know something about what sea levels were. You know what the temperature patterns were. how warm the ocean was, were there corals? There's all kinds of different questions you can learn by doing this kind of analysis that you just can't know just by using sort of climate models, which is our standard framework for thinking about future change. Okay, so let's go through and look at how they actually did this and what the results are. Okay, so this is just sort of a contextual figure, and I think this really puts the future climate change in the geological past, in the context of the geological past. So for context here, the y-axis of this figure is temperature change relative to some average. So this is saying if we take an average of climate from 1950 to 2000 as our baseline, how much warmer or colder were climates in the past, and how much warmer or colder will they be in the future? So the historical period that they use to anchor this plot is right here. And what they're saying is that over the past, so let's see, so this line here is 0, the year 0, I think. And this is 10,000 years before the present, 100,000 years before the present, 1 million years before the present, and 60 million years from the present, before the present. So one thing to notice is that the x-axis on this graph is not linear. So the spacing between here, so here you have 200 years between these two lines, whereas here you have 20 million years. So just keep that in mind when you're looking at this plot. Here, I'll zoom in a little bit more. Okay, so let's look at this plot. So if we think about where we are now, so we're right about here, a little past 2005. So relative to the year 1950, we've warmed about one, maybe a little more than 1 or a little less than 1 degree. And if we look past that, so this is the prehistorical period. So this is sort of this black line. The earliest part of this black line is when we first started doing temperature measurements of the planet. So this is about 1850 or so. So for this period, the climate was pretty stable. We have really good measurements of this. And the climate really didn't change that much. And it's only started to change a lot in the last 50, 100 years or so. And if you go back further to about, the last 10,000 years or so, that's where you start to see that, the climate also wasn't really changing that much. But you'll notice that here the color of the line has changed. So here you have this black line, which is not that wiggly, and here you have a more wiggly green and yellow line. So I don't know which color is which, but these are probably tree ring records. So we don't have any direct measurements of temperature of the whole planet, from 2000 CE to 10,000 years before the present. And so instead what we do is we use these proxy measurements. So proxy just means it's like a stand-in for a real measurement. And so the way you do that is you look at the historical measurement, the historical period where we do have measurements, and you can look at how things like tree rings have changed over this period with temperature. And so, for example, tree rings, so if you're in a cold place, trees like it to be warm. They like warm winters. They grow more in warm winters. And so if the spacing between the rings is bigger, that means that tree grew more in that year. So you can sort of relate the temperature around that tree. And there's some really sort of careful statistical ways of doing this. I don't do that kind of research myself, but I have friends who do, so I know a little bit about it. But if you do that careful analysis, you can do it for all of North America. You can do it for basically anywhere in the world where you had trees and the trees follow some kind of relationship with temperature. And so you can build a line like this and show that climate really didn't change that much over that period. And probably this yellow one is the tree ring record, and then this blue one is some other kind of record. You can do a similar thing with fossils. So fossils of plankton grow at different rates in the ocean, and so you can also get temperature that way. And so if we go back about 10,000 years, further than 10,000 years, that's when you start to get some pretty big climate changes. So if you look at, this is like roughly a little more than 20,000 years ago, you start to get pretty cold climate. So this is basically the peak of the last ice age. So this is the last glacial maximum is what we call it. So it's the most recent time that the planet was at sort of a temperature minimum. So this is where basically the entire North Pole was completely covered in ice. So we're talking not just Greenland, which is covered in ice now, but the whole Arctic Ocean was completely frozen, probably year-round. And also all of Canada was covered in ice. And even where I live in Boston, there was like a mile-thick ice sheet on top of us. That's really tall. That's like if you had ice not just up to the top of the tallest buildings in Boston, but like several times that height. Like if you had ice, taller than the Empire State Building over New York. That's how cold it was back then. And that's just a global temperature change of about -5 degrees. So that sort of gives you a sense that just because, 5 degrees doesn't sound like a big temperature change, if you have that over the entire planet over thousands of years and you sustain it, you can change the climate a lot. This is when like woolly mammoths were roaming the earth, and when there was a land bridge between Asia and America. And so that's when we think like the first, maybe some people think that the first Americans came over from Asia into America through the land bridge. Some people also think they did it on boats from Polynesia, but that's a different question. So anyways, this is the last glacial maximum, the last peak of the Ice Age. If you go back further than that, then you get what we call the last interglacial. So this is the last period that was not an ice age. So this actually turns out, it's kind of interesting. Before the last ice age, this last interglacial, we actually had a pretty similar climate to today, right? The temperature is a little bit warmer than 1950. This line is like pretty much right on what it was like in the last interglacial. And we'll see in the analysis later that when they look at how similar today's climate is to past climates, they find that the last interglacial was really one of the most similar ones. And so what's interesting is if you go back before the last interglacial, you see that the temperature drops down again. And this is another ice age. This is like the peak, second glacial maximum before the last glacial maximum. And then what you notice is that if you keep going back about every 100,000 years or so, you get this cycle where you have these warm periods, these cold periods, the peak of the ice age, warm periods, cold periods, warm periods, cold periods. So these are, what we call ice ages. This is like what the cartoon movie Ice Age is based on. And we've known that this is a really, dominant pattern in Earth's climate over the last million years. We've known about that for a while now. I think since the 60s is, we've known about this for like over 150 years because Milankovitch, in like 1906 was already trying to explain what caused these. That was like when some of the earliest climate modeling started. He like tried to explain what causes these variations in climates based on orbital motions. We can talk about that later. So anyways, if you go back before this record, so now we're going back to like 1 million years, so you still are getting with these wiggles. These are still ice ages and ice age cycles, but now we've changed the x-axis again. So these wiggles are now much more shrunk than compared to here. But these are still ice ages going back basically until about 3 million years ago. And this is where we still have wiggles, but we're getting a much warmer climate. And so by the time you get to the mid-Pliocene, even though you have these wiggles and you have some colder years and some warmer years, you've warmed the planet enough that you're actually no longer sustaining an ice sheet over Canada and Greenland. And so that's what you see up here, this line that says Northern Hemisphere ice sheets. So where it's a full line here, this gray line, that's showing you that there were ice sheets during this period, but before 2.5 million years ago, there's sort of a partial ice sheet, and before 20 million years ago, there's no ice sheet. So once you start to get to these really warm climates of the early Eocene, so we're talking like 20 million to 60 million years ago, you no longer have any ice sheet over North America. Like a picture, no ice over the Arctic, no ice in Greenland, no ice in North America and Canada. And then even as you get back to the really warm climates, like 50 million years ago at the peak of the early Eocene, you have no ice in Antarctica. Antarctica was completely thawed. And if you actually look at sort of the geological and fossil records for the early Eocene, you see some pretty amazing things. If you go up to what is now Greenland or even Alaska or Antarctica, you see that in all three of those places, you find things that we see in the tropics today. So there's things like fossils of alligators in Alaska. There's these palm tree fronds, so like the leaves of a palm tree. You can see these beautifully in the fossil record when you go back to these early periods where it was really warm. And you see these things in Antarctica, where now, it's covered in ice, it's super cold. The only thing that can live there is like penguins and certain kinds of seals. So it's pretty remarkable. This is a really different climate than today. And if you look at the actual temperature change, this is like 10 to 15 degrees Celsius warmer, which is a lot. Okay, so that's sort of the geological record. Let me know if you have any questions about that part, and happy to fill in some things. Oh yeah, so I didn't talk about the right part of the graph, which is sort of the most relevant part. Okay, so we talked about the past. This is stuff we know happened for this period. We've measured it for this period. We've sort of indirectly measured it with these climate proxies. In most cases, you have two lines overlapping each other, which means we have not just one, but several lines of evidence to support these temperature changes. Okay, and then for the future, obviously we don't have any observations because it hasn't happened yet. We can't know for sure what will happen, but we can use climate models to get a pretty good understanding of what's going to happen. So the way climate models work, you take the planet, you break it up into a bunch of little pixels, and you use the laws of physics and the laws of chemistry to basically tell how you're going to move energy and heat around in the climate system, coming in from the sun, coming out from volcanoes, and also emitted, as you change the planet by putting human carbon dioxide and other greenhouse gases and other effects into the atmosphere. You can model all those effects directly based on like the fundamental principles of physics. I mean, we're talking things like, Newton's first law. These go into these models. And so if you use one of those models, you can do an interesting sort of social and climate experiment. What you do is you say, okay, there are three examples of things that humans can do. The first thing we can do is, right away we can stop emitting fossil fuels. We can move to renewable technologies, for example. So these are things like solar panels and wind turbines. They don't emit any carbon dioxide, and they provide energy. Whereas, if you use something like, so that's this dark blue line. That's if you replace, like, over the next 100 years or so, you replace all of our technology for producing energy with renewables, and you change your agricultural practices so that you're releasing less methane. You change the way you build buildings. You build with less cement, which emits a lot of CO2, and instead you start building with lumber or other things. So that's this scenario, this blue one. And so you see there is that actually we warm a little bit until about the year 2050 or so, and then we start cooling down. And if you sort of compare backwards, you see that the temperatures you get to are sort of similar to this last interglacial. So the peak, the warmest parts of these ice age cycles, and you get a little bit similar to some of the Pliocene, but at least you avoid looking like this early Eocene. Okay, so then we can do sort of the opposite experiment, which says, okay, let's pretend we have, in the future, we just completely go all in on fossil fuels. We start, we continue mountaintop removal mining for coal. You just basically wipe out a mountain and take all the coal out of it. You do shale gas in Canada or in the northern U.S. You get these tar sands where you just get all the oil out of these dirty sands. You drill in the Arctic to get all the oil out of there. So this is a scenario where you really go all in on fossil fuels. You're like, you know what? Fossil fuels are great. We don't want to deal with renewables. Let's just burn everything. And in that case, you warm the planet by a ton. So by 2100, you warm it by about 5 degrees on average. Or by 2200, 100 years later, you warm it by 8 degrees or so. And by 2300, almost 10 degrees. And so if you look back at what, there is a big range here. So that's because, climate models are not all the same. Some of them predict, slightly cooler climates. Some predict much warmer climates. So there is some uncertainty in exactly what these futures would look like. But this is the average best guess. And if you sort of map this back into the geological record, so if we draw a line from here to there, you see that in the global average, the climate that looks most like this one is sort of this early Eocene. So remember, this climate in the future is going to look a lot like the climate where we had crocodiles in Alaska and Antarctica and palm trees growing in Greenland. That's kind of wild. So this is sort of a first step at trying to understand this paper. And then they start going more in detail. So now we're going to look at, do I want to do this paper? Or this figure? Yeah, we'll do this figure first. Okay, so this figure has got a bunch of panels. We're going to focus just on this top left one. The rest is sort of more details, which we don't really need to know. So this RCP 8.5, so this is the scenario up here, this red one, where they're burning all of the coal and all of the gas. So this is the let's business as usual, let's commit on fossil fuels and not really worry about climate change. And so what they do here is this kind of clever analysis where they look at, if you take every point on Earth, what is the climate that is most similar to that at that point in time? And then these percentages here refer to what percent of the planet looks like that climate. So what they see is that if you start today, so here, let's see, let me get the label here. So let's see, about 30% of the world looks like the historical period, so that makes sense. The historical period is from 1900 to 2000, so obviously that's the most similar climate because we haven't experienced all that much climate change yet. So most of the planet, or 30% of the planet, looks like historical period. Another about 25% looks like the pre-industrial period. That again makes sense. The pre-industrial period had a pretty similar climate to today, about 200 years ago. And then the third one is the Pliocene. So this is that warm period about 3 million years ago. It's not the super warm one, which is the Eocene, but it's still pretty warm. So some of the world today already looks like the Pliocene. Remember, that's because we've already had a little bit of warming since these historical and pre-industrial periods. And then there's the Holocene. So this is the period of the last 2,000 years. So it's maybe a little bit warmer than historical and pre-industrial, but definitely not as warm as Pliocene. And then some of it looks like the last interglacial. But the key thing here is that today, very little of the planet looks like the Eocene, which is that really, really warm climate 50 million years ago. And then this dark red line is no analog, which just means that in the last 50 million years, no climate has ever been this warm. So obviously today does not really look like the no analog climate. But what they can do is they run these climate models into the future and look at how these things change. So for example, let's just go all the way to 2300. If you run these climate models forward and burn all of your fossil fuels and all of your coal, and you go all the way to the year 2300, 280 years from now, what does the climate look like? So it goes from having 0% or 1% of the climate of the planet looking like the Eocene to 45 or 44% of the climate looking like the Eocene. So this is telling you is that in 280 years, if we commit on fossil fuels, almost half of the planet is going to look like this really warm geological climate where, basically we had crazy warm tropics. We had, most of the species that are alive today couldn't really exist. We had palm trees in Alaska and, crocodiles in Antarctica. There was no ice anywhere, not in Greenland, not in Antarctica. So sea levels would be, hundreds of meters higher. Although probably the sea levels by this period would not be hundreds of meters higher. They'd just be a few meters higher because something like sea level does take a really long time to adjust. Temperatures, those adjust quickly, but it takes a while for all the ice to melt. And so most of the planet, or half of the planet, looks like the Eocene. You get a little bit more of the planet looking like the Pliocene, or about the same as today. But remember, basically what happens here is it looks like the planet's going to become the Pliocene, and then it starts to decrease. The reason it decreases is because the planet becomes warmer, and the Eocene, the really warm climate, starts to replace it. So that's why these sort of switch off. And then I think the most scary and sort of the biggest result of this paper is that by 2300, if you commit to fossil fuels, 9% of the planet has no geological analog. What that means is that if we continue to warm, or if we continue to go all in on fossil fuels, in 280 years, the climate will be a lot warmer than the climate was in the past 50 million years. That's kind of wild. What that's saying is that this entire cooling trend that has taken 60 million years for natural climate variations to cause could be gone in 280 years because we're just pushing so much stuff into the atmosphere. And what they're not showing in this plot is that most of this warming in the past was also due to carbon dioxide. It's just that carbon dioxide was in the atmosphere because of natural reasons. So the concentration of carbon dioxide in the Eocene was something like, I think the numbers are anything from 800 to 4,000 ppm, which is like 2 to 10 times more than we have today. So yeah, that's like the biggest result of the paper. And then this is basically the same figure, but for the medium trajectory. So this light blue is like, what if we, continue to emit some fossil fuels, but we like don't go all in on it. We also have some wind and some solar, but we're sort of halfway between like all in on fossil fuels and all in on renewables. So people like me probably think this is the sort of the most likely. And so in this case, thankfully the no analogs are pretty low. So most of the climate is going to look something like climates in the past 50 million years. The Eocene, so these really warm climates from 50 million years ago, 5% of the planet will look like that. And then about 37% will look like the Pliocene, which is that pretty warm climate from 2 to 3 million years ago. Let me get some water. Okay, so these are sort of the two main results of the paper, I think, or really this figure is like the main result. Then they go into a little bit of the details of the methods. So this is showing like a map of those same figures. So these colors down here, again, refer to the different analogs. And so now you're showing like the spatial structure. So like by 2200, this is the one where this is like all in on fossil fuels. You're seeing that, places like Alaska and Greenland, they haven't really caught up to the warming yet. So they're still pre-industrial and historical climate. So they're really not going to warm like that much. Whereas the Pliocene and Eocene are going to look like these super warm climates from a really, really long time ago, 50 million years ago for the northeastern US. And like, just to sort of give a sense of what that means is 50 million years ago, Boston was really like a tropical place. Like, think about if Boston were more like Florida or like, Mexico or something. Like, this is a really big change in climate for the eastern and western US, for example. And the no analog, so remember this 9% of the planet that's going to have no geological analog. So that's mostly happening in some sub-Saharan Africa, but also, oh man, this is really embarrassing. I don't know my countries very well. I think some of these are Thailand and Bangladesh. I don't really know, Cambodia maybe. So these are the places where they're going to be like, nothing in this region will have experienced that kind of climate for 50 million years. So that's kind of interesting. So if you look at the actual methods, so far I've talked about temperature. The actual methods they use are not just temperature, it also uses precipitation. So it's not just that the temperatures are going to warm a lot like they did in the past, but also you're going to get a lot more rain, which is also what you had in the past. For some regions, and then sort of on average, you're going to get rainier. Some places will have more droughts and be drier. But the general trend is that when you warm the climate, the air can hold more moisture, so you're going to get more rain. That's just sort of like a basic thermodynamic argument. But there's also the fact that, winds move moisture around, and so you have to be a little bit more careful with how you do it. So I really like this paper. I think it's really cool. The first author, Kevin, has been working on this for a couple of years because I saw him present it at a workshop a couple of years ago. And he's a grad student, so this is a pretty cool paper for a grad student to publish. So yeah, I was pretty excited about this paper. I don't know, what did you guys think about it? You guys have any comments or follow-up questions, thoughts? Let me know in chat. Let me just check here. Here, can someone just type something in chat just so I know it's working? Oh, I'm an idiot. It's not working. Okay, my bad. My Streamlabs was not working with... Okay, now I'm seeing all of the stuff you guys are typing. Thank you guys so much. Yeah, Socrates, this is like a really impressive piece of work, and it sort of makes sense to me why, he was first presenting Like, I saw him present these maps basically 2 years ago, and it's not surprising to me that it took another year and a half to get it all together. All right, let's see. ArcD K Wolf says, "Is this paper available to download?" Yeah, so we should have a link to our Discord somewhere, and in the Discord, I posted a link. I'll just post it here. Let me see. I put all these papers in a Dropbox folder, which I'll post in chat right now. Okay, you should be able to download the papers there. You can also get them online, but some of them might have a paywall, which is kind of annoying. All right. Let's see. Socrates. Oh, no. WebEmperor says, in one of the maps, it showed Scotland and northern England having pre-industrial by 2200. Why is that? Oh, that's a very good question, and I actually know the answer to that. So thank you for asking that. Okay. Or I know the probable answer. Okay, so yeah, one thing to notice is that Scotland and northern England, and even a little bit in Iceland and Greenland and sort of the Labrador regions, these haven't really warmed very much, and they still have sort of pre-industrial or historical climates by 2200. The main reason for that is that you have a shutdown of these ocean currents in the North Atlantic, and that acts to cool this region. So even though you have warming basically everywhere else in the world, you're actually going to have a little bit of cooling over here. And that's going to act to basically cool the surrounding region. So, you can see that more dramatically even by 2100. And you see this in all of the standard climate models that people use for like the IPCC reports. And it's a question that I'm super interested in, is exactly why there's cooling there. That's one of the places where climate models have the biggest spread. So even though we're pretty sure it's going to cool there in the North Atlantic, we don't know by how much, we don't know exactly when, and we also don't know how it's going to interact with the melting ice, because we think that when ice in Greenland melts, it's going to actually increase that cooling. But most of the models that are used for these kinds of analyses don't have the ice sheets in the model directly. They're sort of like an attachment. And these models might have ice sheets because they're some of the better models for this kind of thing, but I'd have to check that. Actually, let me just ice sheet model. Okay. There might still be an ice sheet model in these models, but they didn't mention it in the paper. Okay. Socrates says, there's so much information, it'd help if you maybe had a summary outline on screen of what you just talked about. Oh, that's a good point. Let's see if I can think of a good way to do that. Well, maybe what we can do is just read the abstract of the paper. I can zoom in on that and then go through that like sentence by sentence. Maybe that'd be a good thing to do. Yeah, let's do that now. Okay. Can you guys read this abstract, this bold text on the side here? If not, I can zoom in a little more. That should be good. Maybe that's too big. Okay. So first sentence of the abstract. So for those who don't know, the abstract is sort of like where people put the summary of the main methods and results of their papers. So they say, as the world warms due to rising greenhouse gas concentrations, the Earth system moves towards climate states without societal precedent, challenging adaptation. So by societal precedent, they mean that human society, if you want to go as far back as Homo sapiens, have only existed for about 200,000 years. And what this paper is saying is that humans alive in the next couple centuries are going to experience climates that no human has ever experienced. Okay, so second sentence, past Earth systems, states offer possible model systems for the warming world of the coming decades. So this is just summarizing the method they use, where they use models for the future and models of the past to compare the two. These include the climate states of the early Eocene, the mid-Pliocene, the last interglacial, the mid-Holocene, pre-industrial, and the 20th century. These are the periods we talked about with the figures. And here we quantitatively assess the similarity of future projected climate states to these 6 geohistorical benchmarks using simulations from the Hadley Center, the Goddard. So this is the NASA model. The Hadley Center is the UK model. And the community climate system model is this sort of open source model that's run out of Boulder. There's what's it called? The National Center for Atmospheric Research develops it. And these are probably, these are like three of the first models to ever be developed and some of the better ones. So that's a good sign. Under the representative concentration pathway 8.5, RCP 8.5, emission scenario, by 2030, future climates most closely resemble mid-Pliocene climates. So this is that period 3 million years ago, which is kind of warm. And then by 2150, I don't know why they chose that date, they most closely resemble Eocene climates. So this is that period 50 million years ago that was super warm. And just a quick note, this 8.5 refers to basically the radiative forcing that's going to be experienced by 2100, which is just like how much extra power is or energy is going into the Earth system by that date due to greenhouse gas emissions. So that's why this number's there, just so you know. Okay, and so here they say under RCP 4.5, climate stabilizes at Pliocene-like conditions by 2040. So what they're saying here is that, in this really intense fossil fuel scenario where you go all in on fossil fuels, you get a ton of warming and you look like this climate 50 million years ago where there is no ice anywhere. But if you're on a more moderate trajectory, so if you only, let's sort of split your energy into fossil fuels and renewables, your climate will actually stabilize at a much more reasonable climate. So like the one that was still, 2 to 3 million years ago. So it's still a lot warmer than today, but at least it's not the insane climate of 50 million years ago in the Eocene. Here they say Pliocene-like Eocene climates emerge first in continental interiors and then expand outward. So that's just referring to the spatial patterns in those maps we showed. And then this is, I think, the main result of the paper and the one that got the most press and that people have been posting all over Twitter and stuff. Geologically novel climates are uncommon in RCP 4.5. This is the medium scenario, but reach 8.7% of the globe under RCP 8.5, characterized by high temperatures and precipitation. And so for, especially geologists who study the last 50 million years, this is the thing that caught their attention, because this is saying that, you can learn as much as you want about the last 50 million years. It's not really going to be that helpful in this scenario because you're going to warm the climate so much that it won't look like anything in the geological past. And here they sort of arbitrarily take this point of 50 million years ago because there are climates from before 50 million years ago, say 500 million years ago, which are much, much warmer and definitely, that those would be an analog for this climate. But we just don't have that much information about those climates. Fossil records only go so far back. You can only use certain dating methods that scientists use to date fossils. You can only use those so far back. So the further far back you go, the less we know. So that's why they only stopped it at 50 million years ago here. Yeah, so this is, I think, the other big result. Hence, RCP 4.5, the medium scenario, is roughly equivalent to stabilizing at Pliocene-like climates, while unmitigated emissions trajectories such as RCP 8.5 are similar to reversing millions of years of long-term cooling on a scale of a few human generations. So this is key. I mean, this is basically all of the climate variations that happened over the last 50 million years, those are just going to be gone in a couple centuries if we keep, destroying the planet like this. Or the habitability of the planet. Okay, and then the final sentence, both the emergence of geologically novel climates and the rapid reversion to Eocene-like climates may be outside the range of evolutionary adaptive capability. So this is sort of a speculation, but this is where they hope the research will go in the future, is that now that we know sort of what the future climates might look like, let's think about, how quickly do animals and plants evolve. So if we do end up in a future that looks like that, can we actually adapt, or can we just not adapt in that short of range? Okay, let me catch up on questions. Hopefully that was a little more clear, Socrates, now that we've gone through the abstract. Although there's so much information in this abstract that maybe that wasn't sufficient short summary. So I think the main thing to get out of this is that this sentence here, unmitigated emissions trajectories are similar to reversing millions of years of long-term cooling on the scale of a few human generations. I mean, that's the main thing going on here. Okay. MTG Diversity says, one thing that's unclear, maybe I missed it, I joined late, is what the analog means. Is it what the place was like in that time period? Yeah, exactly. I'm going to assume that's Trevor, but I don't actually know. So what they do is they have climate models of the future and climate models of the past, and they basically look at, so I can show you the actual formula they use for how similar they are. So they use this formula here, which is like, they call it the multivariate dissimilarity, but it's basically just showing how different two maps of temperature and precipitation are. And so they apply that to all the different combinations of two models, and they can basically show how similar two models are. Okay. MTG Diversity says, it's not the thermal aspect of ice melting there that causes less warming, is that it interferes with the North Atlantic deep water production, which slows the Gulf Stream. Yeah, exactly. Yeah, I think in one of these literature reviews, we'll talk about the details of exactly how, so this relates back to this question of why Scotland is cooling when the rest of the world is warming, and or not cooling, but it's not warming at all, or not very much. So that has to do with the slowdown of this deep water production, which is this current which sinks water in the North Atlantic, and then it sends it south to upwell in the Southern Ocean. And as you melt Greenland, you're sort of putting a cap on this sinking water here, and that acts to cool this area. We'll talk about that because it's easy to like sort of make a blanket statement like that about how it works, but I think the details of that are pretty interesting, and I think there's a lot of work to be done there, and that's sort of somewhere that I'd like to head in the future. Hey, Nicandria, welcome to the stream. Okay, so Shua1710 says, you lose most of the rocks from 50 million years ago, and you don't understand the paleolatitude very well. Yeah, that's a really good point. Okay. I know that, so one of my roommates is studying a period 600 to 700 million years ago, which is when we had these snowball Earths, and those are a little bit past 500 million years ago. And I know that she's like actually gone and found these rocks herself in places like Svalbard, which is this island in the Arctic, Namibia in Africa, and also in Australia. I think they found these. So there definitely are some rocks that are older, but they're probably pretty hard to find. And yeah, like you said, it's hard to know once you go back that far. Like, just because you found the rock in Africa doesn't mean that it was like at that place on Earth, because the plates have moved so much for that long. You just have like it's just because like you found a rock that you think is in like a warm climate today, you know, it could have been like at the South Pole 500 million years ago, and reconstructing that trajectory of how the plates have moved is still a pretty tricky thing. That's a really good point. I didn't think about that. That's like one of the reasons why doing this kind of study further than 50 million years ago would be really hard. Okay. MTG Diversity says, it looks like they are choosing analogs from potentially any location, not just the same spot. Yeah, that's one thing I wasn't super clear about that formula in the paper. Yeah, I think that they must do something where they only look at like how different the temperature is in a certain region, but I don't exactly understand how. Well, yeah, so this S here is the covariance. So I would guess that probably sort of is weighting stuff in a nearer region, but I'd have to sort of fiddle around with that equation myself to convince myself exactly what it's doing. Yeah, sometimes people use these sort of arcane statistics that they sort of made up for this paper, or in this case, they cite other papers that have used that same statistical method, but it's kind of hard to get intuition for how these things work exactly unless you mess around with it yourself. Hey, Paul Person, Paranor001. Thank you guys all for joining the stream. I don't think I've ever seen you guys on here, so, and you too, Shua. Love having new people on the stream. Okay, so I think that's it for this paper. Does anyone have any last